Hello, explorers, and welcome back to Reach the World's Explorer program. For 25 years, Reach the World has inspired youth to become curious, confident, and compassionate global citizens through the use of virtual exchange. My name is Tim, and I'm so glad you're joining us for today's amazing live stream event. More than 3,600 years ago, the volcanic island of Santorini in Greece exploded, and as one of the largest volcanic eruptions in history, this powerful blast blew the center out of the island, sending rock high into the sky and creating a tsunami impacting the weather as far away as China. And if we fast forward to today, we know that Christiana, Santorini, and Colombo, this volcanic group in the Aegean Sea, which together is known as the Hellenic Volcanic Arc, is particularly hazardous because of what's happening far, far, far below the seafloor. And to better understand the history of volcanic eruptions in this region, the Hellenic Arc Volcanic Field Expedition, which is the expedition we've been following, is currently traveling aboard the scientific drilling vessel JOIDES Resolution into and around the flooded caldera of Santorini and some other sites to collect rock and sediment samples containing over 3 million years of clues. And the coolest part, as always, is that you and I get to join this incredible expedition through this virtual exchange. We have a lot of returning classrooms today. In fact, when they pop up on the screen, you're going to see their Hellenic Arc Volcanic Field Expedition flags flying in the background. Super excited about that. You've been receiving regular reports from Explorer Sara Whitlock aboard the ship, all of which we can still find on her Expedition Journey homepage. I shared a link in the chat for you all. If you haven't read her articles yet, I highly encourage you to do so. We just published another one last night about Sarah's scientist friend Allie and her very special color chart. So if you're curious to know what that is, maybe we'll talk about it today, but it's definitely available as an article at that link. I want to turn things over to Sarah. We're going to connect live with her again today from the ship, especially to take a closer look and more in-depth look at the science being done on this expedition. And as a final note, welcome to all of you teachers and students who are joining us live today or watching a recording. You can always use the YouTube chat bar to let us know you're here, where you're joining from, and of course to share any questions you have as we go. For the classrooms who are joining us live, we'll get you on camera as soon as we can so you can ask your questions directly to Sarah. So without any further ado, I want to bring Sarah back on camera. Hello, Sarah. It's great to see you again. Welcome.
Nice to see all of you. I saw a couple of you right at the beginning before we got started here. Just a quick question before I get going is, can I flip my camera around? I probably should have practiced that ahead of time.
Why don't you give it a try? Let's do it. Give it a try.
Let's see here. I'm attempting turning it off. Well, if I can't, I can just flip my whole screen around so that I can show you everything.
Well, maybe as we get
here. So
as we get started, before you start your tour, can you give us a little update on where you've been since we last saw you?
Yeah, so we've been all over the place. I'm gonna actually go try to find, we have a big map on the wall that I can show you where we've been. That's what, here, let me see if you can see this. Oh, so we have, I don't know whether you'll be able to see that. There we go. That's kind of straight. We've been all over the place. We have these drilling sites that you can see with these little yellow dots. We've actually been, I think the last time we talked, we were at our second drilling site, which was next to the Colombo volcano. And since then we had come, so around Christmas we were here, we came down here, and then since then we've been to every other site for a brief period of time. Right now, we're actually in transit, so that means that we're sailing. So we are going from a site that was down here near the Christiana volcano. So there's 3 main volcanoes we're looking at, and that's Christiana, Santorini, and Colombo. We're sailing from around Christiana back up here to a site over near one of the basins. So we've been back and forth a lot. It's not super normal for an expedition to go back and forth as much as we have, but we're just having a fun time drilling in a lot of different sites. So that's what we've been up to this time.
Fantastic. I think the map's really helpful in understanding. You can even see, and in my introduction, I talked about Santorini, the middle of the island being blown out, and you can see it on that map at the caldera is filled with water. That's so cool. Well, today we're going to talk about science, and we're going to take a little look around the science laboratories on the JOIDES Resolution. So I'm going to turn it over to you.
All right, great. So you've seen a little bit about where we've been drilling on this map. We can talk a little bit more about that, but basically we're trying to learn, as Tim said, about the history of this region. Because we're in transit, we're going to stay mostly inside the boat. I'll show you the main door and like some of the lifeboats real quick before we go into the science lab, just so you can get a little bit of an idea of what it might look like. So this is what one of our doors looks like. So we have these waterproof doors that you open by actually turning like this. It's pretty cool. Keeps all the water out just in case. And then when we pop out here, you can kind of, you can see a little bit of our lifeboat. Unfortunately, I guess it's too dark to be able to see much, but we'll see more of the drilling floor in 1 second. All right, just got to get this door shut. All right, so we are off to kind of the back of the ship where you can see more of our drilling floor. Because we are in transit right now, we aren't actually actively drilling. We only do that when the boat is stopped and in one place. So we can talk a little bit about what our drilling setup might look like before we go outside. And please interrupt me at any point if you have questions. So I'll show you this little diagram over here. Let me know if you think that it's straight at all. It's a little bit hard to do this with the front-facing camera. So we are in this big ship that you can see at the top right here. That's us in the JOIDES Resolution. And when we get to one spot that we want to drill at, we use 12 motors to stay in place. I don't think we've talked about those yet, but those are called thrusters. So those are these motors right here. You can see them in little dots kind of on the bottom of this boat. And those motors help us stay right in place over the spot that we want to drill on the ocean floor. And then we stick this big series of steel pipes down to the floor, and we push down into the floor with the weight of those big pipes. And sometimes if we're drilling into really hard rocks, we'll use a drill bit that has kind of big teeth on it. And I will show you what that drill bit looks like in a minute. But now we're going to go outside and see some of the top of our drill. And to do that, I have to put on some safety glasses and my hard hat because there's a lot of big moving parts out there. So we want to make sure we're staying safe. All right. All right. So here we are out on our drilling floor. You can see, let's see. You can see a little bit of what we're working with here. So we have this big yellow thing right here is our motor. That's what's going to turn our big long drill string that we stick down to the ocean floor. It doesn't have any pipes connected to it right now because we're not actually drilling. But if you see those two long sticks with circles on the end of them, those grab onto our drill pipes that we stick down onto the ocean floor. And this big machine over here, this one right here, I don't know if you can see that quite. There's a big red machine that has a little thing like this that's right here. That is actually what puts together our big steel pipes. So that is going to help us connect everything, and each steel pipe that we use is really, really heavy. It weighs about 1,900 pounds, and it's about 30 feet long. So that's what we use to get down to the ocean floor. Once we're actually down there, and we stick a big straw into the ocean floor to collect our sample. So we're going to go look at this place called the catwalk. So this is where the scientists bring the samples once they have collected them. And the straw that we're going to stick into the ocean floor is actually down here. So it looks like this. And you can see it's a big long straw. Before we cut them, each one of those straws is about 30 feet long. Then they get cut into sections that are about 1.5 feet long. So we'll cut a bunch of those different sections. And we do that actually, and we make sure we mark which side is up and which side is down. So we use different colored lids for each section to mark which side is up and which side is down. Does anybody have any questions so far?
All right, it's a good chance. If there are any early questions about the drill or about the process of collecting samples before they're even really analyzed by the science team, let me know. Teachers definitely anyone who's on camera is welcome to just raise a hand, wave at me if you want to ask a question, or if you're in the chat, be sure to drop it in there. It looks like we have some very attentive listeners right now, Sarah. I don't see any waving hands just yet. Oh, wait.
Right, so
Sorry,
we
I think, Sarah, we've got a question from Miss Ketteridge's class. If you're ready, go ahead and unmute yourself and you can ask your question.
How far do you drill down to get the core samples?
Speak up, Philip.
That's a
How
great
far do
question.
you drill down to get the core samples?
How far we drill down is what I heard. So we actually can drill super far underneath the ocean if we need to. We can drill down as far as 5 miles under the ocean. We're actually not doing that on this cruise. We're only drilling down a couple hundred meters. So for our purposes, that's very shallow. That's not very deep for our boat. But that's because we're really close to a lot of islands. So we're not drilling quite as deep because the sea is much shallower when we get close to land.
Yeah, that was a wonderful question. Sarah, just to clarify, when you say 5 miles, do you mean 5 miles below the surface of the water or 5 miles below the surface of the seafloor?
That's combined. So it's about 2.5 miles below the surface of the water, and then another 2.5 into the surface of the ocean floor itself. Yeah, it's very deep. We don't do that really ever. That's usually not the norm, but that's theoretically what we're capable of doing. A lot of that depends on what the seafloor is like. If it's really hard or if it's really sticky, those can keep us from drilling as deep as we'd like.
All right, great. That was a great question. Anybody from Friend School or Miss Hockenjoss class? You'll have to be like really, yeah, there we go. I see a wave from Friend School. Let's bring them on. If there's a question, please go ahead.
Does the ship and the drill just stop? And then you just sleep?
It does. We do. We sleep right on board. That's a really good question. And it's actually really unique to our ship to be able to stop in place like that. We have 12 motors underneath the ship. So we have one in the back that we use to go forwards, like a normal ship. But then we have a bunch of extra motors that we use to stay in place. And we have a bunch of beds on board. So we each have like a comfy little cabin that we sleep in at night.
All right, excellent question. I can see these students are really thinking about what you're talking about, Sarah. So maybe we can do the next. Oh, another question from Kettridge School. Go ahead.
How deep is the crust where you're drilling?
How deep is the sea floor where we're drilling? Is that what you asked? So right now we're about 300 meters beneath the sea floor. So if you remember, each meter is 3 feet. So you can, I think that's like 900 feet beneath the seafloor. I'm really bad at mental math, so if somebody catches me doing it wrong, please correct me. But yeah, that's about how deep we are. So if you can imagine your favorite roller coaster at the amusement park, a lot of times the really big ones are like 200 feet. So it'd be like 3 roller coasters stacked on top of each other is how deep we are right now.
That is very deep. Great question. We have a question from Mrs. Hockenjo's class. I see you waving there. Thank you for your patience. Go ahead.
What kind of rocks and sediments have you collected from the ocean floor?
Well, I think I heard what kind of rocks and sediments have you collected so far? Maybe this is a good segue into the next portion of the tour.
Yeah, this is a great segue into the next portion of the tour. I'll say that because we're studying volcanoes on our cruise, we've been finding a lot of pummices, which are produced by volcanoes, and a lot of ash that gets spit out by a volcano. But we actually have some special scientists on board who can tell you more details about those types of sediments and rocks. So I'll take you inside to talk to them and see what they're doing.
Great question.
All right. Oops. Sometimes it's big thunk from these doors. So now we're inside what we call the core lab. I'm going to spin you around so you can see some of that. So this is a big laser that we use to label our samples. We put each of the samples in a rack that looks kind of like this. These aren't actually samples that we're using on this mission, but because we're in transit, all of the samples that we just collected got put away. Usually they live over here for a little bit right after they come up from the ocean floor. We have to wait until they come to room temperature before we can start taking measurements on them, because some of the measurements that we take get affected by the temperature. So this is kind of where they sit for a little bit right after they come up from the ocean. And then we zoom over into this part of the lab where we take measurements on the whole sample when it's still in a circle. So you can see that we have these samples, that are circles when they come out like this. But eventually we're going to split them in half so we can look at everything that's on the inside so that we can see all of those different layers that we're collecting. But first we take some measurements on them when they're still a full circle like this. And that happens over here in this section. And so a bunch of our measurements actually take place on this big track. And it does all kinds of stuff. But the big thing to notice is that we measure what types of radioactive isotopes there are. So this is just measuring, it's not radioactivity that's scary. It's just measuring some of the radioactivity that's not bad for you that comes out of the sediments and the soils. And we measure the magnetic properties of the whole sample, and we see how fast sound actually travels through the sample, and that happens over here. And you might wonder, why are we doing all of that? And actually, we have a scientist here who can tell us why we care about taking measurements on the whole sample.
Oh, of course.
So this is Dr. Manga from University of California, Berkeley. We have a couple of different elementary schools.
Oh, excellent. So nice to meet you. So why do we make these measurements? Before actually drilling into what's at the bottom of the ocean here, we used a variety of waves we make at Earth's surface to look inside the Earth and to interpret those measurements that we make from moving sound through the Earth. We need to know how fast the sound moves through that material. And so we can make the measurements on the material we recovered from the bottom of the ocean and relate our images to what reality is like.
That's very cool. So it sounds like we're trying to compare the map that we made before the expedition with what we're finding while we're in the expedition. Does anybody have any questions about that for Dr. Manga?
All right, chance to ask. Dr. Manga, are you what type of science is your specialty? Are you a geologist?
Yeah, I'm more or less a geologist who studies volcanoes, and I use geophysical techniques. Yeah, I'm at the University of California, Berkeley.
All right, fantastic. Students, you have a chance to ask practicing geologists who's on an expedition a question about geology. If you have a question, you're going to have to be real, wave your hand really big so I can see you. You also are welcome to take it all in. I know that was a lot of information about using sound waves to analyze. I think maybe Friend School, are you waving at me? Yes, all right, Friend School. Hello again. Good.
Hello.
Go close, yeah, right here. Then you can.
Have you ever seen a volcano erupt?
Oh, many times. Yeah, in Antarctica, in Japan, in Hawaii.
Have you seen an ice volcano erupt?
Italy.
Wait, is that
Have I
even a
seen an
thing?
ice volcano? I have not, but you know where the biggest ice volcano is? It's on a moon of Saturn, a moon called Enceladus. And it has an ice volcano that's so big that it erupts and makes one of the rings of Saturn.
Wow.
Cool.
That's amazing.
Thanks.
Yeah, so next, if you ever can see the rings of Saturn, think that one of those is made by an ice volcano.
Amazing. It's amazing to think that the study of volcanoes, both on Saturn in our solar system and also underwater and above water, all have sort of parallels. And do you use the same tools to study each of these different types of volcanoes?
Tim, the answer is sort of yes and sort of no. Obviously, in the outer solar system, we don't collect samples.
Right.
And we use spacecraft. But the physics and how things work are the same. And So the tools are slightly different, but the ideas behind them are the same. Actually,
Right.
I think almost all the you're kindergartners, right?
No, older than that. I think we have some upper elementary and
elementary.
middle school students with us today.
Okay. But, some of your students may have gone to the hospital to get an MRI scan or an ultrasound to see what babies look like before they're born. And the tools used to image inside a human body are the same that we use to image the inside of the earth.
Wow.
So if you know what an ultrasound is, we're essentially doing something like an ultrasound for the earth.
Very cool. Doctor, thank you so much for telling us about what you do. Before we let you go, I need to ask you a question that students often want to know. What's your favorite thing about your job?
That we discover things that we never knew were possible.
All right. Well, that sounds like a good job. Thank you so much.
Thank you.
All right, bye. Amazing. Such good questions. Love to see those. We're gonna head now so we've taken measurements on the cores when they were a whole circle, and now we're gonna go to the place where we cut the cores in half before we see what's inside of them. So this is our core splitting room over here. Hello. We have a couple different elementary schools with us. So these are the people who would actually be splitting the course in half, right? And doing a number of other things, which is very cool. You can say anything if you want to, or I can just show.
Yeah, this is where we split the cores. If you can see this big machine over here, we put the cores right here, and then there are two ways that we split it. One way, we take a wire and we pull the wire through, and the wire is actually so sharp that it's able to cut through the entire core. The other way is that this is actually a giant saw on wheels, and the giant saw on wheels will just cut through the core, and that's what we do when we have really hard rock.
Very cool. Thank you so much. So now we'll go see what the cores look like once they've been cut in half. So then they come over here, and we have two halves once we've, cut down the middle. So we take samples from one half, that's called our working half. And then, and we've got some working halves right here. This is what it looks like once it gets cut in half. And maybe we have here Evie and Iona with us, so maybe they can tell you about how we take samples from our cores.
Okay, well, this core that's out on the table at the moment, it's mostly pumice. So it's lots of small particles of pumice. It's quite small up here, and then the particles get bigger and bigger and bigger. And so we take samples, and because this is a loose sediment, we normally just take something like a spoon, a very professional looking spoon, and then we just dig them out, and we put them in a little jar or container, something like this, but maybe a bit bigger. And so that's what we do when it's a loose sediment. And then we measure the weight, and we dry it, and we measure the weight again, and then we measure the volume, and that tells us the moisture content of the sediment, and it tells us the density of the sediment. And that's an important physical property for interpreting things like how fast seismic waves will travel through sediments like this, or how well they can conduct heat energy coming up from within the earth, for example. And because this is a sediment, we use a scoop. But sometimes if we have a harder rock or a harder sediment, we have something a bit more sharp, and sometimes we have to use a hammer. And so it can be quite destructive. So we're only allowed to do this on this working half of the core. So on the other table, there is the half that will be preserved in the archive, and we're not allowed to touch it with our hammer or our knife.
That makes sense. So why might we want to know all of the moisture properties of this type of core?
Yeah, okay, so it helps us, for example, if we do a seismic survey, it's very rare that we get to drill a big hole like IODP is doing and actually physically get the rocks and the sediments and have a look. So often we have ships that go and put out a synthetic seismic wave called a P wave, and that travels down through the sea, then down through the sediments and the crust, and then it bounces back from different layers of sediments and rocks, and it comes back and it's recorded by the ship. And then you have to estimate the properties of the rock in order to understand what that is telling you. And if you know things like the moisture content, then you can find out the density of the sediment. If you have a very dense sediment, then the seismic wave travels faster. If you have a low density sediment, then the seismic wave travels much slower. And then you can interpret how thick the different layers are and what the general structure of the crust is.
So Dr. Mango is describing this to us as kind of like an ultrasound that we use to see underneath the sea. So it sounds like what you're doing is making sure we can accurately compare what we're seeing to that ultrasound.
Dr. Manga was looking at the whole round core, and so here we can be more specific, and we can take just a small specific part of the sediment and measure its moisture and density, and we can check that the whole round core measurement is accurate. Or if we find something unusual in the whole round core, then we can say, okay, so what is it about this sediment? Is it the size of the particles? Is it the mineralogy? What is it that gives it that property? We can do that here when we actually take a physical piece of the core.
Amazing.
But the ultrasound analogy is exactly right.
Yeah, that's great. Does anybody have any questions about taking little samples from our cores that we could ask Iona?
Yeah, students, anybody who has a question, let's take advantage of our chance to ask an expert. I have one quick question while students are sort of raising their hand. And if you want to just come up to the camera in your classroom, if you have a question, I'll see you coming towards the camera. But my question is, based on that like 1 meter section that you're looking at approximately, do you have any idea about how much time, how much history of the seafloor is represented in that section of core?
That is an absolutely brilliant question. And what we do, so if in this particular core, you picked an interesting example, because this is made of pumice, and we assume because we just have pumice, we don't have any clay layers or other sediments. So we assume that this pumice could have been made in potentially one eruption. So that's in a geological timescale, then this meter was made instantly, potentially. But if you had come and we had a different meter, you might have seen a clay, an ooze, and we have lots of sediments called oozes, and you might have seen lots of different stripes of color, and they in the same length. That might be a much longer time to accumulate all that material. And that's why it's so important that we have specialists in fossils, microfossils that we find in the sediments, and they know at what time in Earth's past those fossils lived. And then if we get the age of the core from that, we can work out, okay, so how long, what was the age at the top of the core? What was the age at the bottom of the core? How long to accumulate this material? So those guys are very clever.
Fantastic. I see some students who are eager to ask their questions too. I'm going to bring Miss Kittredge's class on. We've got a young man who looks ready to go.
What's the biggest question geologists are attempting to answer about volcanoes and earthquakes in your research area?
Ooh, that is a fantastic question. Okay, I'm going to speak from my research. So I'm a volcanologist. I'm studying volcanoes, but I am especially studying submarine volcanoes because, of course, it's much harder for us to see eruptions that happen underwater. And so sometimes we don't even know that an eruption happened. And then maybe we go and we pick up some rocks from the seafloor and we have to say, okay, when did this erupt? How did it erupt? Was it a big explosive eruption, or was it just a gentle kind of oozing out of lava or magma? And so this expedition is a fantastic way to test different ideas about how submarine volcanoes erupt, because we have lots of submarine vents in this area over time. They've made lots of different deposits, and so we're going to be analyzing them and comparing them to the same kind of pumice material made by island volcanoes. And what's same and what's different, and what does that mean for how dangerous they are, and how they happen, things like that. For me, that's the big question. But there are many big questions on this cruise.
Fantastic. Yeah, thank you for that great question from Kittredge. Like, it's so cool to hear the big idea, but then see how you actually get the clues, as it's been described before, to answer those questions through those core samples. I'm gonna move that class off screen so we can welcome the Friend School in Boulder back for another question. Go ahead.
How many samples do you get a year?
We'll get in 1 year. Ooh, that's a great question as well. So I'm a scientist that lives and works in Japan. I grew up in the UK, but I work in Japan, and I often go on research cruises. So maybe I have 4 research cruises per year. But luckily, they're not all quite as long as this one. This time we're on board for 2 months, but maybe my normal cruises are 2 weeks. But I think, how many samples in a year would that be? At least 100, maybe 200. Yeah, it's a lot. And then I have to analyze them when I get home. So I'm very busy.
Fantastic.
What a good question.
Another great question. Ms. Hackenjost, is anybody there would like to ask a question? I don't want to leave you out. You'll just have to, I see a hand raised. Fantastic. Come on up. Go ahead whenever you're ready.
I was going to ask you, where will you place the puzzle tab of the...
I didn't quite hear you. Could you say that again?
Where will you put the puzzle tab of the tubes?
Where will we put the cap?
What are you going to do, I guess, with all of these collections that are in the tubes? What do you do with them after you leave the ship?
With all these cores, with all the tubes?
So, yeah.
Oh, that is a great question. So every single core that we collect, we wrap it up and we store it in a tube, and then they go to a big storage facility, and there are 3. Okay, there's one in Germany, in Europe. So any cruises in Europe like this one, which is in Greece, all of those cores go into this big warehouse. And there's another one in America, and there's also one in Japan. And I've been to the one in Japan, and you go into this huge building, and from the floor all the way up to the ceiling, and every single part of the room, it's just rows and rows and rows and rows of cores. And so they are stored for many years. And if you ever want to look at a core that has been collected on a previous expedition, you go to one of these 3 centers, and they will get the core out, and then you can have a look. You can ask to take a sample. You can reanalyze things. So they are all kept very safe for future people like yourselves. If you grow up and you want to analyze these cores, you can make a request and come and take them out of this kind of library, a library of rocks that have been collected. So, yeah.
Fantastic question. Thank you so much. I see one more question from the Kittredge group. They look like they're ready to ask it, so I'm going to let them go ahead.
Are you monitoring the current emissions of gases like carbon dioxide and sulfur dioxide?
Oh, great question. So for volcanoes, as you say, it's really important to monitor them to understand their activity, and gas emissions is one of the key ways to do that. And certainly they are monitoring the gas emissions on Santorini, so the volcanic islands. They have monitoring in place. It's not our job on this cruise, but scientists are doing that. And then even underwater, for the submarine volcanoes, like Colombo volcano that we are studying on this cruise, other researchers, you met Evie briefly earlier, and she is a specialist for Colombo volcano, which is underwater. And they take a robot that has a video camera, and they dive down into the volcano, and they can see the gases coming out. And so they measure the temperature of the gases, they collect samples, and then they see how it changes over time. So yes, it's a very important task, and there are lots of researchers focused on doing that.
Fantastic. Another amazing student question. Thank you so much. I'm sorry, I didn't catch your name. Can you tell us your name, please?
Hi, my name is Iona McIntosh, and I think I said I'm from the UK, but I'm working as a scientist in Japan.
Fantastic. Iona, thank you so much. This has been a great stop on our tour of the JOIDES Resolution.
Thank you so much for so many great questions.
Yeah, so many good questions. Thank you all for all of your questions for Iona. So we were talking about the working half and all the samples that get taken over there. We don't actually have any, we do have some archive halves over here. And actually we have another amazing scientist named Susan who can tell us about that. And I know, Susan, we had a question earlier about what types of rocks we're seeing. So
yeah, right.
I knew you would be the right person for that.
Yeah, I don't know how much you've talked volcanic eruption products. So have you heard of the word pumice before?
I think I said something about pumice, but I didn't really explain what it was.
Okay, so these are all pumices. Presumably there was a volcano that had an eruption that took magma, and there was all this expanding gas that caused the magma, the molten rock, to just explode. So imagine if you put a bunch of little pieces of styrofoam inside a soda container and you shook it up and took the lid off, all of that material would burst out and explode. So this kind of material exploded out of a volcano, landed on the seafloor, got buried by lots more eruptions, and so we've been pouring into that pumice. And so this is, compared to some of the other things that we've described, this is pretty straightforward. So what we're doing is as we describe the core, is we, one, have to decide what color it is, and in order to, what's that? Sorry.
I was just going to say, we talked about this a little bit ahead of time about the color chart, so they're extra interested in the color chart.
Okay, so yeah, so we could look at this and just say, oh yeah, it's kind of gray looking. But this color chart gives us very specific ways to define colors. If there's a little bit of a green hue, or if there's more of an orange hue to it, so that we would pick a color. In this case, we are using this page, the gray one. We choose a color. We're kind of on the really light end of the spectrum, and then we go over to what that corresponds to, and there's a name to it. There's if we chose this one up here, that would be a white, and then this would be a light gray. But if we had decided it had a little bit more green hue to it, then we would choose one of these. This would be a light greenish gray. So anyway, we end up having a lot of discussion about what color the rock is in the core that we're describing. So we describe the color. We also describe the sizes of the particles. So if you can see, there's kind of a range in sizes from really small pieces of pumice to bigger pieces of pumice. And then this one, there's a lot of ash in here. The pumices are so fine that you can't really see them without a hand lens or with a microscope. So that's all important to describe those sizes. There was a really nice core section here a second ago. I guess it just got taken. Maybe you can see it through the plastic. There is an amazing little chunk of rock in here. So there's all pumice, but then there's this one little layer with lots of different colors. Can you see something shiny in there? It looks like gold. I don't know if you can tell on your screen. It's called fool's gold. It's pyrite. So that during this eruptive event, there was all this pumice coming out of the volcano, but then somehow it just picked up also these pieces of rock that may have been lying around or were on the side of the volcano along the vent, and the eruption just picked those up and carried them with them and then deposited them down. But that was pretty exciting. We had a lot of oohs and ahs and a lot of people taking pictures of the fool's gold in that piece there.
That's so amazing.
Anything you want to ask me?
Any questions about how to describe the cores, the types of rocks we see in them?
Sure, Susan, we've met a few of your colleagues in the science lab. Can you just describe what your specialty is and maybe how it's different than the work that some of your colleagues that we've met have explained?
Yeah, so I'm a volcanologist, and the way that I do my work, some people are what we call physical volcanologists, where they're really interested in the changes of grain sizes or the size of the little vesicles or bubbles inside the pummices. But my interest specifically is the chemistry and also the little minerals that are contained in these pummices. For me, those minerals are really exciting because if I look at the chemistry of those, or if I look under a microscope, I can see little growth rings on minerals. And those tell me about what's happening underneath the surface. So I can tell stories maybe about what triggered the eruption, how long the magma was in the magma chamber underneath the surface, what caused the volcano to erupt. So my specialty is geochemistry, and that helps me understand volcanic eruption processes better.
Fantastic. I got to ask my question. Now, students, if you have any questions for a real life practicing volcanologist, this is so cool. I can see you in your classroom. Step up if you have a question. It looks like Ms. Hawkinjos has a question, and we'll bring you right on. Go ahead.
So when you're like drilling, you like accidentally hit lava and like does it break?
I think the question, if you didn't hear that, is have you ever been drilling and accidentally hit lava and broken the drill? Is that a good summary of the question?
Yeah.
What you're saying?
Yeah.
Yeah, so did we ever hit molten lava while we were drilling? The question is no. I mean, the answer is no. And I think that would not be a very good thing if we did, because we would probably destroy the drill. But they take really good care. We take really good care to not drill into an active magma chamber. Although I did hear a story once about in Iceland that they did drill into the edge of one, and so things got quite hot, but they were able to get the drill string out right away. But I think they take really good care to make sure that we're not drilling anywhere near magma.
All right, fantastic. Thank you for that great question. Kittredge School, I think we got a question. Go ahead whenever you're ready.
I was wondering what was the average terminal velocity of like magma and lava bombs that comes out of the Colombo volcano?
That's such a great question, and I don't know the answer to that because being a geochemist, I don't do this physical properties. But you know who would know that? Are you going to talk to Michael?
We did talk to Michael. Do you think? Yeah, we could go over and ask.
Yeah, he would be the person that would be able to answer that question. So if you hold on to that one, maybe you can take them back there.
Yeah, we can go ask that one. Great question.
That is a great question. It is so rare and amazing to ask everything you've ever wanted to know about volcanoes. And if the person we're speaking to doesn't know the answer, there's someone right around the corner who might.
Exactly. So. And I do the same thing. I mean, I'm sure there's, there's some good things to think about with that question because the particles are coming through air or through water in some cases. So I'm guessing Michael will have a great way to answer that.
We'll loop back around to that. I see someone at Friends School in Boulder, Colorado, who's got a question. We'll let her go ahead.
How often do you find fool's gold or like rare rocks when volcanoes erupt?
I couldn't get the question.
Here, get closer.
How often do you find like fool's gold and like different rocks when volcanoes erupt?
Yeah, so that's a great question. So some volcanoes, all the material that erupts out of the volcano is just the magma that when it breaks apart and explodes. But other volcanoes, especially if it's an eruption after a long period of quiet, then it can pick up all kinds of pieces of foreign rock. Sometimes there's sedimentary rock, sometimes there are exciting things like this fool's gold or some bright blue metamorphic rocks. So it really depends. Different volcanoes behave differently, and even within one volcano, if it's been quiet for a long time, you might get some really exciting different kinds of rock. If it's been erupting for a really long time, well, then maybe you just get the volcanic rock, which is pretty exciting to me, but not as exciting to some other people.
All right, wonderful question. Thank you so much for asking. So Sarah, I think we're sort of, I can see classrooms that are maybe like having to go in and out to recess or other things. Is there another stop on your tour you'd like to squeak in before we run out of time? Thank you so much, Susan.
Yeah,
okay, thank you.
Much. Yeah, so I was gonna take, if we have time, I'll take everyone to see the microfossils that we use to talk about how old our different samples are, but I don't know if people have to go.
Let's do it. I want to see some microfossils. If classrooms, if you can stay with us, fantastic. If you have to go, we totally understand. You'll be able to see the recording or the end of our conversation afterwards. So stick with us if you can, but if you have to go, thanks so much for joining us. We're going to look at some microfossils and then we'll wrap things up.
Amazing. So this side of the laboratory, you can see, has a bunch of microscopes in it. Let me see, get myself oriented correctly. And this is Adam, one of the scientists who works with microfossils a lot. And so he's looking at a certain section of each core sample to find where the microfossils are and what their identity is. Maybe you can tell us a little bit more about how that works.
Sure, yeah. So after we get the core up on deck, all the sediments from deep down below in the on the ocean floor, it comes up looking a little something like this. So it's just kind of rocky rubble. So what I'll do is I'll take this sediment and I'll put it into hot water and hydrogen peroxide and other chemicals to break it down into a really, really fine fraction, like very, very fine kind of sandy sediment, which will look a little something more like this here. So there's the camera there. So it's kind of like fine grained at this point. And I'll take this sediment and I'll sprinkle it onto one of these trays here. And basically I can do it now actually quickly. So sprinkle that on there like that, and so it looks pretty much like a little bit of sediment, and actually there's sand grains and lots of small grains and whatnot in there, but actually what's in there as well is the single-celled skeletons of tiny little plankton. So my primary job on the boat as a micropaleontologist is to look at fossils using a microscope, and what I do on the boat is provide what's called biostratigraphy, which is basically using the fossils that are in the rocks to find out where we are in time. So a good example of that is if you were looking in a rock and you found a T-Rex tooth, then you know that rock is probably around 66 million years old. But instead of looking at T-Rexes, I look at these single-celled tiny organisms, and once I've found them, I use this paintbrush here, which is one of the smallest paintbrushes you can buy, and pick them up individually. And you need a very steady hand, and I need to make sure I haven't had too much coffee, or else my hand shakes a little bit looking under the microscope. And then I'll put them in this machine over here. So this machine is one of our two electron microscopes on board the ship, and I'll use that to take electron micrographs, which come out a little something like this. So here are some of the fossils that I look at. They're a little more intricate than a grain of sand, and if we look at, let's say, this fossil here, this is called Globocanella puncticulata, and this scale bar here, this black bar, is 1/3 of a millimeter. So these organisms are very, very, very small. And this organism in particular is extinct. It went extinct around 3 million years ago when the northern hemisphere, the Arctic ice sheet was forming. So that was probably something which led to its extinction. So in the same way that a T-Rex tooth would tell me that a rock is 66 million years old, if I find this organism in that rock, it tells me that it's 3 million years old.
Amazing. Thank you. Does anybody have any fossil questions for Adam?
That is amazing. Absolutely. Thank you so much for sharing that. I have a lot of questions, but I know we've got our two classes who are still with us. If anybody has any questions about how we use those samples that come up from the ocean floor to determine about what time they're from. I see maybe somebody from Kittredge, who's ready for a question.
I want to know, do you find anything else, like fossilized other than plankton, or is it just mainly plankton?
That's a really good question, actually. On this expedition, we've actually found a whole fossil fish in the sediments, and also we found some plant remains like leaves and grass, which it's around 2 or 3 million year old grass preserved in our sediments, which is something you don't normally find within these kind of in the deep ocean. And we get lots of when I'm looking in my samples for these tiny plankton, we also see lots of fish teeth and fish bones and lots of little small bits which just fall down to the ocean floor as time goes on. Yeah.
Fantastic question. Thank you so much for asking. I see a question coming from Mrs. Hackenjoe's class. Go ahead.
What is your oldest fossil that you found?
Say one more time, please.
What is the oldest fossil you found?
The oldest fossil you've ever found.
That I've ever found. Well, not on this ship, but once I went to the Sahara Desert in Africa, and I found some dinosaur teeth, which were around 100 million years old. So a lot older than these fossils here. Yeah.
And maybe to continue that question, what's the oldest fossil you found on this expedition?
On this expedition, we found some fossils which are about 6 million years old. So still very, very old compared to how old we are. Yeah.
All right, fantastic. Thank you for that great question, Ms. Hackenjoe's class. Excellent. Sarah, I think we're right just about at time, so maybe you want to wrap things up.
Sounds good. Thank you so much,
Thank you.
Adam.
Bye-bye.
Thank you, Adam.
Yes, we made it to most of the major stops on our tour, so I'm just gonna, if you want to, I can show you one of my favorite spots on the boat before we sign off.
Yeah, let's do it.
The pet wall. So our pet wall is right at the lab here. You can see a bunch of pictures of people's pets, which we want to look at because we're on the boat for 2 whole months, and people get sad and they miss their special little friends. So that is my very favorite special place to hang out on the boat. But
Sarah, you
yeah,
froze for a
that's
minute
pretty
when
much-
you were showing us the wall. Can you show us the pictures one more time, please?
Mhm.
Yo, everybody's cute pets. Amazing. Well, Sarah, this has been an amazing virtual field trip to the JOIDES Resolution with you. Thank you so much for lining up such great experts to answer our questions and taking us through the whole process of getting a core onto the ship and how it's broken down and analyzed. Students, you got to get most of your questions answered during the stream today, and I know many of you have to go and do other things. So what I'm going to do is bring you all back on screen one more time. And if you want to unmute and give Sarah a big wave. All right. Thank you so much, everyone, for joining. Make sure you check out Sarah's new article on the Journey homepage. And we're going to have one more chance to connect with Sarah on the ship. So make sure you join us next time. I'm going to look up the date so I don't get it wrong. It's Tuesday, February 7th at 12 o'clock p.m. Eastern will be our final live stream with Sarah from the JOIDES Resolution. So everybody have a great day. Sarah, wonderful to see you. Thank you so much. Bye, everyone.
Thank you. Bye.